Hello, hello. I hope I'm audible. Mm, the guy is not showing up. I think I'm live. Alright, so today's plan is to learn more about transformers. And right. Anyway. Wait, so I want to learn transformers very well. So that's what we're going to do. Right. So I call it a deep dive into transformers. So my plan is to uh, like learn what transformers is and then use like Hugging Face or something else to play with it a bit. Uh, then I watch Andrea Karpathy's videos and I want to use his code to implement a transformer on my own. With his help, with the help of his code, with his code as a foundation, how to make a basic transformers and then make probably a small LLM. After that, I have to start reading papers. Vastly reading. These are just paper ideas for paper. Yeah, that's the plan. That's the current plan. So yeah, that's today's plan. So today will be the first part of that. Okay, why are you still not loading? I mean, live. I have no idea. But this is looking fine. I think this is a bit too high. Yeah, hopefully now it's better. Probably now. Hopefully. Okay, anyway, we'll continue. So yeah, that's the plan. So first, I think it's best if uh, I start. Okay, this is a implementation from some random YouTube video, right? Okay, it's from my video. So we'll probably try to read this. I don't know how much we will get, but that's okay. This is how to need paper. Summary. Okay, this is summary for transforms. So I think I'll just read this. Hmm? We'll try to learn about transformers. I've read the paper about once, but it's not an easy paper to read. So we'll see. We'll see. Right. Anyway, and this is already right. Okay. Introduces transformers. What is transformers? A new architecture that improves our RNG. Okay. Uses attention mechanism. In fact, it uses self-attention mechanism. Drops RNs in concepts, improved parallelization, figures out global dependencies of input and output. Yeah. The ability to understand long-range dependencies in a network is far superior to other models. Last time checking that I'm okay. That's self-attention. Self-attention, sometimes called intra-attention, okay, is attention mechanism relating different procedures of a single sequence in order to compute a representation of the sequence. So the encoder takes in the input along with the position encoding and convert them into uh, hmm, I think it creates key and value, right? What is key and value? Key and value are vectors for each of the input in the for all the input in the context length. We'll see. I almost solve it. Encoder one on the left. Encoder maps an input sequence of symbol representation to sequence of continuous representation. Encoder maps an encoder maps an input sequence of symbol representation to a sequence of continuous representation. Symbol representation. What is it? What is integer question mark? It comes of there are six identical layers. Okay, each layer has two sub layers. Oh yeah, these layers. Okay. The first is a multi-head self-attention mechanism, and the second is a simple position-wise fully connected feed-forward network. Okay. There is a residue connection around these two sub-layers followed by layer normalization. Okay. Decoder is the one on the right. In addition to the two sub-layers in addition to the two sub-layers in each encoder layer, the decoder inserts a third sublayer. Okay, no, these are the same. Which performs multi-head attention out the output of the encoder stack. The first is the multi-head layer. Towards the encoder, we employ a residual connection. Okay. We also modify self-attention sub-layer in the decoder stack to prevent person from attending to subsequent person. The masking combined with the fact that the output embeddings are offset by one position, ensure that the predictions for position I can depend only on the output of the position less than I. Okay, that makes sense. Okay. In the inserts third sublayer. Attention. Okay. Attention function can be described as mapping of a query and key. Okay. So attention. What is attention? Wait, what is this? This would be an array, right? So query. What is a query? So we have some text, right? Let's say, and we have this is our context length, let's say, right? Our whole context length. These are tokens. Okay, let's say this is our input token. For each input token, there will be a key value. Or will there be a query also? No, there's no value. There is a query and a key. Query is used to ask questions to every other token, and key is to answer the question asked by any other token. So, intuitively, how self-attention happens is we take in a token. In fact, we take in the query of the token. We multiply that query with the key of every other token. We matrix multiply it. It probably also requires transposing, right? Yeah. also requires transposing, but I'm going to ignore that fact right now. Right. And when we do that, uh, we get a score. uh, it is kind of like dot product actually means alignment, right? Like similar things when we dot product similar things, the dot product value is higher than that of say less similar things. What I'm trying to convey is that query like dot product with key, actually key transpose, this will give a array. No, this will not give an array. This will give a similarity score depending on how similar these two are. So higher similar means, and this similarity score is used to calculate the attention. Now, for consistency, this will be divided by the dimension of the query, right? Dimension of the query or key, all of them have the same dimension. This is just dividing a scalar quantity by a scalar, doesn't have any like meaning other than probably improving the quality. Thus, we have a score. Now we take the softmax of the score. We make into probabilities. So we'll have an array which will give the probability of each word attending to our query, etc. Now we multiply this by value. If I matrix multiply, I mean, what is that called? Cross product and dot product. We dot product just by value. Value matrix is also a trained parameter. I don't know if there's a value matrix for each. Is there a query key and a value associated with each token in the context? For and for not. Yes. Each token in the input sequence has its own query, key, and value. These circuits are generated as follows: input embedding, linear transformation, attention mechanism. Right. So each of them has a value also. We multiply that with the value, and we will have the attention scores. Sure. Each token doesn't inherently have fixed QT. Okay. Just the opposite answers. Funny. For each token, the model first learns say, okay, these combine when transform to three separate linear, these transformation happen at each attention net. So each token actually gives multiple sets of QK. Okay, I mean, yeah, sure. That's what I meant. Okay, that makes sense. Sure. I mean, we will just move on. We have more to read and we will figure it out. The attention, okay. Attention of QKV. Multi attention instead of performing a single attention. D model and instead of performing self single attention. Instead of performing single attention with the D-dimensional key value. The D-dimensional key values where we found it beneficial to linearly project the query key and values with the fetch time with different learned linear projections to DK and D dimension. Probably DQ respectively. Each of these projects are versions of QKV perform attention function in parallel. In dimension these are concatenated once again projected resulting in the final values as depicted in the figure. Okay. I think I will read attention for unit paper tomorrow. Yeah, I think it's best if I let this thing. We'll do something else today. We'll continue learning something, some other things. Right? It will be let's move on. The encode decode attention level. In encode decode attention, the query comes from previous decode level. Memory key and value come from output of the encoder. This allows every person in the decoder to identify all person in the input sequence. Person encoding. Since our model contain no recurrence or convolution, not okay, we cannot use of order. We inject information about the position. In this work, we use sine and cosine functions of different get more detailed output information available at this point. Yeah, we patch it. I think we'll go here. I think this is a flat thing, right? Okay, inside the okay, so good summary. Okay, good now. So this is in AI notes, right? I think I'd like to read that. NLP attention. Yeah, I mean, we'll just very fastly read through this. NLP. Oh, I know what is NLP, data acquisition, blah blah blah, feature giving evaluation. Okay, now a word embedding representation of text as numerical vectors in order for just ensuring that this works. Okay, cool. Okay, statistical representation, bag of words representation. Vocabulary is formed. Okay, we will form such a vocabulary. One-hot encoding. We will take the same thing and convert them to one-hot form. Distributed representation, that is using neural networks. Word embedding. So these are learned embeddings. Instead of treating words as description, the embedding allows to manipulate them to continuous vector and higher dimensional space with hidden patterns and relationships. I kind of want to put this in quotes. Right. Distributed representation of words in higher dimensional vector space, where words with similar meanings are represented by similar vectors. Not by similar vector, with the are represented closer vectors. That would be better, right? Okay, cool. Word embeddings. Okay. It refers to the process of representing categorical data such as okay. Representing categorical data such as words, lower as continuous vectors and lower emphasis. Okay, sure. The unsupervised learning method, often called self-supervision, avoids the need for any sort of hand-labeled supervision. Okay. Physics and engineering. Yeah. Everything was software engineering. Okay. So we can do things like man is a woman is king to what? We use similarity like cosine similarity. Embedding methods. Methods like combined word embedding. To get the embedding of a word, we matrix multiply the embedding with the one hot vector. Easy. Word to vec. It is a specific algorithm for learning a word embeddings from a large corpus of text. It was developed by Google. The two types of word to vec. Skipgram and continuous bag of words. Skipgram a word to vec embedding. Type of word embedding used in NLP tasks. Okay, here the model predicts the contact given a word for skipgram. And in continuous bag of words, we try to predict a word from this surrounding words. Glove, glove. I think occasionally order, right? And my audio seems kind of off. I'm not liking it. Can I do this right now? Hello, 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 hello. Okay, I cannot do that right now. Uh, okay, can do this. Filters. Hmm, what about now? The audio could be better right now. It could genuinely be better right now. I don't know for sure. Okay, I'm fine with that. Let's work with this, right? This is fine. Okay. Anyway. Okay. Contents bag of words. Contents bag of words. Glove. We have problems. These are fine. But don't have. These are fine. What do you even mean? Glove is a global vector. Okay. And the word embedding model that works by learning continuous vector approximation for words simply capture semantic approximation. Okay. Blah. Statistics instead of neural networks. Statistics. Okay. Glove is statistical based. Okay. Problems. These are fine, but don't have contextual person understanding. Why would I? They don't have contextual person understanding. Therefore, we use better. representation, right? For taking similarity, cosine similarity is bad. Oh, really? All vectors tend to point in one direction. And so we have to standardize this vectors, and the problem is not solved by standardization. Is a cosine tends to underestimate human judgments and similarity of word meanings for very frequent words. Okay. Language models. Sequential models, okay. Language models, okay. They can be statistical or neural web based. Just ensuring one last time. Statistical language models. Statistical language models are the type of language models, models that use statistical patterns. Uh-huh. Oh, okay. It contains n-gram model, which is a probabilistic model used in neural network. Okay, it predicts the next word given nth word given n minus one word. So now given n minus one words. So a bigram model takes in two words. Predicts the next. Okay, we use means okay, and the probability is we can multiply up the probability. I'm pretty sure I've made this. Yeah, we just take in the huge. We just take in a lot of text and create the data set for the n-gram model, and we just train this. That's now, yeah, it's a simple structure. Markov assumptions that the probability of what depends on the previous one. Okay, this is made throughout in transforms, right? Uh, what is happening? Uh-huh. In transformers. Okay, neural network based language models. Neural language models use neural networks to predict the likelihood. Okay, then okay. Evaluating language models. Okay. How do we evaluate? First is extrinsic, basic, like just using it. Then is intrinsic base. Primary methods are perplexity, U-score, ROC score, word error, right? F1 score. Intrinsic improvement probably doesn't guarantee an extrinsic improvement. Okay. Obviously, perplexity of a language model is on a test set is inverse probability of the test score. Inverse probability of the test set. 1 hour probability. Okay. Normalized by the number of words. Oh, okay. We will read this. So we will take in the probability of for each word, and then we will take the nth root. N is probably the length. Okay. Nth root of the reciprocal of the probability. So probability is a number less than 1. Inverse probability would be a number very greater than 1. Probably because we are just multiplying these numbers. So this is going to be a very big number. We take the nth root, so we'll get an H number. Okay, that makes sense. Law probability is better. I can do stuff. Bilingual evaluation under study is a metric used to evaluate the quality of machine generated translation. Generated translations, okay, primarily in the context of machine translation task. The blue score number between 0 and 1, with the 1 being perfect match. Okay. Use score cannot be used for like other tasks. Dealing with out of vocabulary. Smoothing, you apply smoothing, add case smoothing, add small numbers. Back of interpolation. Okay. NLP concept, some random concept. Edit distance, encoding, encoder. The encoder command converts pre-processed text into embeddings. The encoder layer helps to create contextualized representation of the input sequence. It processes the input sequence in the encoder layer is responsible for processing and generating can be parallelized. Okay. TF idea PPMI. Okay, we'll just move on fast. Teacher forcing. Here constantly using the actual answer as previous data. Professor Forcing model trains as a mixture of true previous and its own previous. Okay, says, I don't know if it's bad. Probably Professor Forcing with the bit, with the very low previous, like correct value. Wait time, negative sampling, logic lens. I don't know what that is. Logic, I mean, wait time is a way of tying the weight of generally encoder and decoder to reduce RAM usage. The negative sampling is, yeah, if this is the data, we give negative samples. Logic lens is a method that allows us to create a vector from any layer. Vector from any layer of the transformer and pretend that it is a pre-final embedding. Then you multiply this by unembedding layer to get logics. And you can compute the softmax. This specifically used in transform-based model. It lets to understand that the model wasn't trained to predict the internal awareness without maybe always for okay. Gaining into model's behavior. Okay. It is a technique method I used to take it like okay, I mean it doesn't say why you have to use it, right? It lets us understand the level of understanding. The model. RNN. Design the reference patterns. Okay. So we have loops here. It's actually like this. So we given an input. This is a really good image. I love this image. So we given an input, and we multiply that input to create h1, and this h1 is used to generate. This h1 will have information relating to all the data here, and this h1 will also take in the h0 from the previous layer. So this will be used here. This will be used here. Thus, the hidden layer will contain information from the current input and also from the hidden layer of the previous input. So we will take both of these guys to produce the output. And that's how inference is done in RNN's training. Backpropagation through time. That's the coolest name in all of machine learning. To update model weights and biases, to do this, we do self-supervision to predict the next word given early ones. We do inference for each word in the text. Okay. Disadvantage of RNN. Vanishing RNN, explaining it easy. Bidirectional RNN. Okay. Okay. We have LSTM, long short-term memory. So this is the LSTM. We have hidden state from the previous timestamp. Also the current input. This is a forget get. This is used to forget from things from the long-term memory. And then we add information to the short-term to the long-term memory from using input get. And then we give in the output and hidden state for the next state. And output comes here. Yeah. Yeah, GRU, which is a simplified version of LSTM. I think I like better GRU. GRU architecture. Yeah, this is a better picture. This is a better picture. We have an update get and a reset get. Update get updates the data. Reset gets resets the earlier data. Encode decoder mode converts input into fixed and numeric representation called context. This will be used. Okay. Such a system converts input into fixed length numeric representation. Uh-huh. The encoder decoder model. Okay. We have the encoder which creates the context, and this context will be used by the decoder. Okay, so we know the transformation encoder decoder model, right? The following is the simplified encoder decoder model. Okay, we have input text. And this is an RNN. Okay, this is a really cool image. So we have we input text to the RNN. This will be this is a hidden layer. And for the next hidden layer, we take in the input. This is the embedding of the input. We multiply that with a matrix. And then we take this also. And both of them together is used to update this. And eventually here we have the input is complete. Right? So we will give in a separator. And when the separator is given, I mean, at each term, the output is generated and we just ignore all of them. And here, the context is complete, right? This have information about all of these guys. The problem with this thing is this is a bottleneck because however large the text, however large the input, all of the information from the whole input have to be summarized, have to be compressed into this one what do you call it, hidden layer. It's not good. It will act as a bottleneck. That is why in the future we do attention. We'll come to that later. So then we put in the starting symbol. It will generate the first word. So this is actually the translation. And this translation will be the input of the next one. I will continue translating. Yeah, so this is our encoder system, and this is the embedding, and this will be the decoder system. All right. Wait, this is not an encoder decoder system. This is a normal system, right? I mean, I'm not sure though. I don't know if it's actually is is this an encoder decoder system? Yes. Okay. Okay, so this is also the encoder generates context. The simplest version of the decoder would take the state to the first hidden. Okay. The decoder would then auto-regressively generate sequence of objects. Okay. A formal version. So simplified, not formal, not very formal encoder decoder model. Okay. This is the encoder decoder model. So in this we have the embedding, and for each of the output we take in the input from the embedding, from the last layer, from the embedding, and from the input to generate the output. So all of these things. 1 second. Uh, okay. So each of these will have access to the uh, okay. Each of this will have access to the context, unlike this one. So this is probably better. This is obviously better. Now training. How will you train this? Right? Right. Training. Training is data is a pair string in the form of source and target. Forward pass is performed, loss is calculated. The order will be loss will be the average of individual losses and backward pricing. These are what it's done. Okay. I mean, it's like very okay, cool. Attention, if attention. In normal encode decoder setup, the context must represent absolutely everything about the meaning of the source text. Yeah, this will act as a bottleneck. A way of allowing the decoder to get information from the hidden state of the encoder, not just the last hidden state. We need to dynamically take in information from each of the input data. We have to devise any system which can do that. And that system is attention server. Attention provides a dynamic vector that is derived from the encoder's hidden states with the unique version calculated for each of the decoding units. Dot product attention, use dot product to do that. Learning attention using neural networks. Another way to calculate attention is to define a set of learning or attention stuffs. Antibiotic algo attention to define a set of weights which learns use during training about how to give attention to each of the encoder. This is a period to dot product attention mechanism. Define set of weights which will learn during training about how to give attention for each victim. Attention and self-attention. Basic attention mechanism. Okay, what is the difference between attention and self-attention, right? Attention versus self-attention. Attention. Attention mechanism allows the model to focus on different parts of the encoder sequence, and the self-attention is a specific type of attention where the elements of the encoder is encoder sequence attend. The embedding in the transformers are being updated dynamically using the surrounding objects. Yeah, self-attention is used to update the position, not positional embedding. I mean, yeah, I'll just call it embedding. Yeah. Okay, now we will talk about transformers, the main feast. Before that, I'll just take a break. So, give me a second. Guess I'm audible. Give me a sec. Just to ensure that this thing works properly. Okay, that's all. Now, let's move on to the big one, right? The boss, transformers. So this is the transformers architecture. So what is a transformer? Transformer is a machine learning architecture. It's a deep learning architecture used for sequential data, sequential problems. So it is a revolutionary neural network architecture which introduces self-attention mechanism that enables the model to importance, weigh the importance of different elements in the sequence dynamically, and also incorporating posture embedding. Transformers capture the sequential order of the input. The architecture comprises of encoder decoder structure where the encoder process input information and the decoder generates output. Multi-attention and enhance the model's ability to capture diverse relationship by employing parallel attention mechanism. Layer normalization and residual connection contribute to stable and effective training. Feed-forward neural network further refine the information extracted through attention mechanism. So this is a very nice summary of transformers. Why? Initially using processing text data, now we can do all solid data. Advantages. Parallel computing means faster, higher context can handle bigger data, better understanding means better quality. I don't know what this means. You can better understand the data, probably, which means the model quality is higher. Better understanding of data, better quality of model. Cool. The transformers architecture. Input text is organized by methods like byte pair encoding. Yeah. What is byte pair encoding? What is input text? What is tokenization? Tokenization is the process of converting text into tokens. What is byte pair encoding? It is an encoding strategy. It is a tokenization strategy in which we'll have a lot of text and we tokenize the text based on the frequency of based on how frequent the text comes. We tokenize the most frequent text. This means that the more frequent text comes as different pairs. This is probably better, right? Yeah. Or is the other way? I'm not sure. Byte. But. Byte pair encoding. Byte pair encoding is subvert tokenization algorithm commonly used in NLP. Char with character level. Okay, I was wrong. I thought it was what is its opposite? Byte subvert tokenization is character based tokenization. Okay. I think I confused byte pair encoding with this thing. So byte pair encoding starts with character level vocabulary, count pair frequencies, merge the most frequent pairs, and repeat the process. Okay, that's cool. I mean, I don't want to put that here, so yeah. So we tokenize the text. There's an encoder decoder architecture. positive encoding also. Context of the input is captured using self-attention mechanism with QKV. Self-attention is performed parallel in multiple ways. Feedforward helps to process output, machine is done using training. Further optimization for stabilities and performance. Layer normalization, rest-based connection. Self-attention is used to update embedding of input words in order to include the context. Other replaces as tokens. The key innovation of transformers is the self-attention mechanism which enables the model to capture long-range dependencies in the data, making them well suited for fast and model sequences. It is a mechanism that updates embedding in order to allow the models to consider context. During self-attention, the model computes a weighted sum of the embeddings, where the weights are determined by the attention scores. These attention scores reflect the importance of each word in the context of the current word being encoded. Thus, the embedding for each word is calculated dynamically with the help of the words around it. Okay. Each input word is factorized using techniques like word to vec. I'll just make you token. Factorize using technique. Thus, word would be rich in context, but will lack context or information. Thus, the tokens will be. This goes into the sequence of encoder blocks, which will use QKV to add the context to meaning. Below things happens in one head. More about it below. Update. Okay. So what happens in self-attention? So for self-attention, we take in the QKV. So update the embedding. So what is the embedding? I started using Vim key binding. Sure. It's a mechanism to occur self-attention. Is the embedding in a transformer, the UKV? Yes, sure. Go search. The transformer, the embedding. I should not use the canvas is something for this stuff, such stuff. Embeddings are used to calculate the QKV. These vectors are derived through learnable linear combination applied to the input embedding. Okay, learnable linear combination. Okay, these are essential different. Okay, so QKV. Okay, that is information permeated. These are also contain matrix of the head. There's a query key value matrix. That matrix is this diagram is added to a previous sample. Now use of typically market dimension. Other dimension. This is I'm audible, right? Yeah. It is a bit low, but it works. So yeah. The QK mechanism is typically used in multiple heads in to enhance model's capacity to learn. Right? So each head has the different given a text. Each head theoretically, conceptually asks a different question, and the query key answers it. Question embedding in quality. Okay, questionable embedding. This happens right after converting the text into embedding before self-attention. We are inherently okay. I get it. Encoder decoder. I don't talk about the normalization or pressure connection here to focus on the encoder decoder part. Okay. shown the image input draws on the sequence. These encoders do multi-head attention and pass the output through feed-forward neural networks. All these will give a particular representation of input. Yeah, I'm sure. If I connection or chain output will combine with bandwidth of the relative. Cool, cool, cool. Nice. Yeah, but this. Yeah, this is a paper. Oh yeah, I remember. This is a very good paper on transformers. I kind of want to read the summary too. Sequencer model. Auto recursive generation. Okay, so text is generated from the previously generated using the previously generated text, and the everything in the context, right? It is auto regressive generation. We generate like this. Sequence model searching. Best word from okay. We will have that. Then we'll search for the best word. Yeah, I can do greedy search, probability search, top case sampling. Well, I take the top keyword, top P sampling, top P probability, temperature sampling. So we have e raised to z by sum of x1 of these things. We divide this by the temperature T. Constant zero means very stable and less creative. Constant one means when Drunken distribution decide reshape the distribution. Higher value make the distribution more and more unique. Temperature in soft max. Yeah.
Beam search. Beam search algorithm is an extension of the greedy search designed to find mask like frequently. It is beam with param. Okay, okay. Sure. Training a transformer. To train a transformer, we use a self-supervised learning algorithm. Okay, in self-supervised learning, there's no ultimate answer in a golden eyeball. We simply train it to minimize the error. We use techniques like each of us in buffer person. The quality of model depends on model non-brain. Data size and comparing power. Bidirectional transformers. Neat transformers are fine, but when talking about like sequence classification, since they have all the information, the key architecture is the bidirectional. We don't mask the future targets. Oh, that's it. Okay. This means the model has access to full context. Trade-off is that this architecture cannot be used for real-time auto-adjusted text understanding since the model requires full input. Okay. LMs. LM stands for Large Language Models. It's a type of artificial intelligence model that is trained on the massive dataset to generate human-like language understanding and generation capabilities. Okay, that is fair. Why don't you give a good examples for LLMs? BERT is an encoder-only model. GPT is a recorder-only model. We know the rest, right? Now we don't know the rest. BERT is a bidirectional encoder representation from transformers. Okay, it's a language model developed by Google in 2018. Key innovation of BERT is bidirectional transformer architecture, which allows the model to capture both forward and backward context representation. So it is an encoder-only model. The thing is, this actually is used has two steps. I mean, its training has two steps: pre-training and fine-tuning. So for pre-training, we train it right in two ways. First one is mask diagram. We mask 80% of our text, and we try to predict that mask word. And we also have next sentence prediction. Giving two sentences, we decide if one sentence is a continuation of the second. Then we fine-tune it on the text. We need to fine-tune it down. You also have GPT, the very popular GPT, improving language understanding by generative pre-trained transformers. So, oh, yes, and this paper introduces two-step LLM training, pre-training and fine-tuning. Okay, record knowledge tutorial has record. GPT, this is the GPT architecture. We have the text mask multi-self attention. We then normalize it. Pay for, yeah, the same one as the recorder, except for the recorder actually has one more part, right? That's so much. Yeah, cool. Then we have some tokenization, basic tokenization, sentence piece, which is a supervised text tokenization, record, detokenize, say, rival useful penalty. Internal section subword tokens. We have byte pair encoding and word piece unigram. Byte pair encoding potential developers will go to complex text. Okay. It's all by computing unique. Okay. First we have very basic character level. Okay, increase. Word piece. Algorithm Google search, never open source. It's have a small vocabulary size like BPE. Okay. The main difference is the way they pair. Instead of selecting a most frequent pair, word piece can be a score for each by using the following formula. Okay. Tokenization of the word piece. Only sites on the final vocabulary, not the merged from. UDgram. It is employed as a tool, okay? It starts from a big vocabulary and removes. Okay, this is what I thought. Byte pair encoding was earlier. Okay, cool. Fine tuning. Another model specific task. This training will later freeze. Generally, we don't finish. We retrain the model or make the minimal adjustment. Okay. classification, we all can like classify that if you want, whereas sequential labeling depends on a topic. I mean, if you don't read that, I don't think so. All good. Cool. Now that all of that is done, what will we do now?
Now what can we do? Mm, hmm. I think now we can try to rate this. Not good. Try to read. No, I think I'll do that in the next stream. Probably the next stream is going to be very soon. So yeah, bye.